Hi guys, this is Mrs. Gassler, and in this video we're going to talk about refraction basics. There'll be another video later for what happens, what we can use that for in optics with lenses. So we're going to go ahead and get started. Over there. Alright, so when we're talking about refraction, there we go. What we're talking about is the bending of light as it passes from one medium to another. And this happens, it's due to a change in speed. At this point, I've probably talked to you about Romeo and Juliet and why they turn when they get to the sand pit is because one of them slows down. In order to think about refraction, what we talk about usually is the index of refraction, and this is just a number that gives an indication of the relative speed of light in that material. So what we're always comparing to is the speed of light in a vacuum. So to find the index of refraction, which is just a lowercase n, we take the speed of light in a vacuum. That's what C is, speed of light in a vacuum. And if you're not sure, that's 3.0 times 10 to the 8th meters per second. And we divide that by the speed of light in the material, whatever material we're talking about. And since this is always less, because the fastest it can go is in a vacuum, then this number is always greater than 1. So n is always greater than 1. If you get a value for n that is less than 1, you probably did something wrong in your calculation. So, some information about what that means. The bigger your n is, that means that this number is smaller, so you have slower light. You're dividing by a smaller number, and the smaller your n is, that means you're using a bigger number, and so that means you've got faster light in that medium. So that's something that we use to think about what's going on. So let's talk about what happens when it's going from fast to slow and slow to fast. Oh, and something useful, it's not always stated, but n of air is 1.0003. It's almost the same as if it were in a vacuum, so it's very close to 1. In fact, some people round that to 1, and that's fine. You can do it either way. I think in my calculations I used 1.003. Alright, so when you go from, let's do one of these at a time here. When you go from fast to slow, first off, we're talking about refraction, so we've got to have a normal line. So there's our normal. And when light comes in at some angle, remember we had Romeo and Juliet, when it gets to the slower material, it's going to turn this way. So this light is going to bend a little bit closer. So you can see here, these are where we're measuring those angles. We're getting closer to the normal. Okay, so I'm going to write that down here. When light slows down, it bends toward the normal. Okay, it always bends toward the normal. When it's going from slow to fast, we still have to have our normal line here, that straight line. This is our normal. And when it comes in this way and it gets to speed up, this side speeds up first, and so it bends this way. So here we've got a bigger angle. So this one, when light speeds up, it bends away from the normal. Away from. Okay. Now, there's this guy named Snell who did a bunch of this stuff here, and he, through experimentation and whatnot, was able to come up with Snell's law. And Snell's law just relates the angle of incidence, the angle of refraction, and then I'm going to use a fancy word, and the indices. It's a plural of index, of refraction of each material. Okay, so Snell's law looks like this. It says that n1 sine theta 1, remember theta is the symbol we use for the angle, is equal to n2 sine theta 2. And the reason I'm using 1s and 2s here is because it's a little easier to keep it straight. So we're not thinking about reflection here. It's just a tad bit easier. With these signs of the angles and looking at these pictures up here, you can tell that if I move this out more, that's going to get bent further, and the furthest that it can bend is going to be that 90-degree angle. So we call something the critical angle. The critical angle is the angle of incidence that causes light to bend 90 degrees from normal. Okay. A note here, this is always when we're going from slow to fast. So if your N2 is smaller, that's what we're going to be talking about. Okay, so the critical angle, and the way you would solve this for is that you want your angle of refraction, so this the N2, yeah, you want this to be 90, and then what would your angle be? So we'll do some practice with that. Once this happens, all the light, when it's exceeded, if you exceed the critical angle, then the light is reflected instead. And we call it internal reflection. Reflected. ED, okay? We call that internal reflection because what happens is the light, it just comes back instead. So it's internal reflection. It stays inside the material, okay, that the light was in the first place. So let's do some examples. In order to be successful at doing examples or doing problems with refraction, you're going to have to know where the sine function on your calculator is. It's a pretty easy one to find. So we're going to do a couple of practice problems here. Our first practice problem is this, and feel free to pause it to write that down. Light travels from air into an optical fiber with an index of refraction of 1.44. Which way will the light bend? And if the angle of incidence on the end of the fiber is 22 degrees, what is the angle of refraction inside the fiber? So it fails to tell you in this question that the index of refraction of air is 1.0003. But I told you that, and so sometimes you're just going to have to know that it's 1.003. So let's go ahead and set this problem up here. N1 sine theta 1 equals N2 sine theta 2. And I might draw myself a picture. So I've got air, and then I've got the fiber optic cable. And it says, okay, so this is N is 1.0003, and this N is 1.44. That means I'm going to a bigger N. So when my air comes in, or my light comes in at 22 degrees, it's going to slow down, which is going to make it bend toward the normal. Okay, so that's the answer to question A. A is toward the normal. Okay, which way will it bend? It will bend toward the normal because it has to. It's going faster. Okay, so for part B, now I'm going to use this equation here. It doesn't matter which side you put the air and the fiber optic cable on, as long as you keep the ends with the thetas matching together. And so the 22 and the 1.003 go together, so I'm going to put those together, 1.0003, and the sine of 22, and then 1.44, and the sine of theta 2. So theta 2 is what I'm looking for here. So the first thing I'm going to do is not plug stuff into my calculator because I don't like to do that. I'm going to divide both sides by 144 so that I get the sine of the angle 2 over here all by itself times the sine of 22 divided by 1.44. Now to undo sine, there is a button on your calculator, and it's usually right next to the sine function. I'm not sure how well you can see this, but it says sine here. Right here it says sine with a -1. That is called the arc sine, and it's undoing the sine. It's opposite of sine. So what you're going to push is that sine to the -1 button. So at this point I might go ahead and actually plug something into my calculator. So I've got 1.0003 times the sine of 22. At this point, it might be good to make sure that you're in degrees and not radians. And then I'm going to divide that by 1. Hang on. Let me do that a little bit different. 0.0003 times the sine of 22. I'm going to divide that by 1.44. Sometimes I just like to make sure that it's doing things the way I want it to. And so that is the number. So I've got 0.26. I think that's a 0. Yeah, 22. That's going to be the sine of this angle here. So then I'm going to do the opposite of that. Sine minus 1 and sine minus 1. So I'm going to use that button on my calculator. And I'm going to type that number in. Actually, I'm not going to type that number in. I'm going to use this lovely answer button because it's so much easier. Okay, and so there is my answer, and it's 15.083. So my angle of refraction is 15.083 degrees. Now I might round that to like 15 degrees and that's fine. But that is definitely smaller, which I predicted because it was going to go toward the normal. Okay. So let's look at the next question. A light ray passed from water, which has an index of refraction of 1.33, to an unknown solid. The angle of incidence is 52.4 degrees and the angle of refraction is 42.1 degrees. What is the index of refraction of the unknown solid? So here's what I've got going on here. I know this is water and it's got a 1.33, and this is a question mark, and I don't know what the index of refraction is, but I know that it's coming in at 50 some odd degrees, 52.4, and that it's coming, when it comes out, it's a little bit closer to the normal. So this is 42.1, which means that this is the little n, because what it's doing is it's slowing down, right? And so this will be the big N. So my n should be bigger than the 1.33. Okay, I'll be able to identify this material knowing the index of refraction, which is actually something that people do. Okay, so I'm going to use my equation, n1 sine theta 1 equals n2 sine theta 2, and this time instead of looking for an angle, I'm looking for one of those n's, so it'll be a little easier to punch into my calculator. Alright, so I can pick whichever one I want to be whichever one, so I'll go with this 1.33, and that goes with the angle 52.4. And 2 is what I'm looking for, and that goes with the angle of 42.1. So I'm going to divide both sides by that 42.1 sine. And so my index of refraction will be 1.33 times sine of 52.4 divided by the sine of 42.1. And I get 1.57. Oh, my 5 and my 7 got stuck together. Let's do that. 1.57. So that's my index of refraction right there. I didn't box that answer either. Okay. And I was right. It is bigger than 1.33. So that's a good way that you can think about whether or not your answers are reasonable. All right, I want to do one more example with the critical angle, and then we'll be done. Okay, so this question says, what is the critical angle of diamond when it's surrounded by water, or air, and then water? So what we're looking for... So we've got our material here, our diamond, and it's going into air, but we want all the light to come back in. So what angle would this have to be to get that 90 degrees here? Okay, so my diamond is 2.42. Whoops, 42, and this angle is what I'm looking for. And air is 1.0003, and I want the angle to be 90 degrees. Okay. Now, conveniently, if I remember, sine of 90 is one of those easy numbers to work with. Oh, it's 1. So this boils down to n1. So this is 1, right? So I just have to divide by 2.42. So sine of this angle, I'm going to put C for critical, is whatever 1.0003 divided by 2.42 is. And then I got to undo the sign, so it'll be sine of -1. Remember, that's what we're doing to get that undone. So 1.0003 divided by 2.42, and then I got to do the arc sine of that number, and I get 24.41. So that critical angle is 24.41 degrees. Okay, that's in air. Now the second part wanted to know about water, so I'm going to do the same thing, just with water instead. So I'll have 2.42 times the sine of whatever that critical angle is, and water is 1.33 times the sine of 90, which is just 1. So I'll divide both sides by 2.42 again. So the sine of the critical angle will be whatever 1.33 divided by 2.42 is, and I get 0.549, blah, blah, blah. I'm going to do the arc sine of that so that the critical angle, that's a C, critical angle of that answer, there we go, 33.33 degrees. So you can see when light is going in from a diamond into air, it has to have a smaller angle. Remember, if we go anything further than that 24 degrees, that light will be totally reflected inside. So that's actually what happens when a diamond, when you shine light in a diamond, it just bumps around inside there until it comes back out. It's pretty cool. So that's how you find the critical angle. So if you have any other questions, make sure you let your teacher know.